Let me explain something else, which is called the Lorentz force. And in this apparatus, I have electric charges coming out of here, and they ionize the gas and make it glow green. So you've probably seen something like this before. Now, this is a magnet, a really strong magnet. So this is put in a little, 36mm camera so that it doesn't clang against other things. And if I put that close to this, you can see that the beam of electrons coming out of there, giving that green glow, is deflected. It goes up if it's near this pole, and it goes down, if I turn it round, for the other pole. So the effect of a magnetic field, if the electrons are running this way, is to bend it upwards. Now, I could do the same experiment, this one, and now I put a sheet of metal, this is aluminium, and I'm going to put this sheet of metal in the way of the magnet. Now, have you got the beam still there, Brady? Because I'm going to put this close to the metal, and I'm not cheating you. Take the metal away, it's still there. Put the metal there, and it's still bending. The magnetic field goes through the metal. Any metal, when it's behaving normally, will allow magnetic fields to penetrate it. The question posed by Edwin Hall was, what happens if you have an electrical current down a wire, as in these wires, but I've blown it up so you can see it quite clearly, and I put a magnetic field near it. Now then, you've seen already that if there is an electric charge running along in this direction, a magnetic field will make it bend. So the charge is going along here, and it's going to go and bend, and suddenly it hits the wall. So if I now think about a wire such as this without a magnetic field, and let's pretend this is a charge carrier so you can really see what's going on. I mean, this is not really to scale. Here's a bit of the wire, and the charge goes through here, flowing down the wire, and the current is just the number of charges moving down the wire per unit time. So if I put a magnetic field down here, and the charges are coming along, as you've seen from this experiment, it's going to bend up and come to rest on the edge of the wire. And if I do this straight off, and then send another one down, it too will do this. Well, now I've got negative charges there, so I'll cancel them out with positive charges over here, and down will come another one, and it will suddenly say, oh, I want to go here. And there will be a positive charge induced on the other side. So now when another charge comes along, it wants to be attracted this way because it wants to go near the positive charge, but on the other hand, there's a magnetic field which wants to sweep it that way. And the balance of these two means that it doesn't choose to go that way or that way, it just carries on down the middle, not being attracted to either side. And as a result, after these charges have built up on one side and the other, it gets to the steady state. So more and more charges can come through just as if this wasn't there. So there's no reason to expect that there's any effect at all. The current carries on flowing. It's just like water going down a tube. You don't know that there's anything happening on either side.